Okay, so hello everyone. My name is Ziad. I'm the newest member of the D3R team. I'm a postdoc, and today I'll be going over our Protein Ligand 2016 Challenge overview. So first, I'll be going over the dataset that was provided by Barry and David that was just presented in the previous presentation. And then we'll be going over the instructions that we gave participants for the challenge, and then the challenge results in our analysis, and finally some conclusions that we could draw from this analysis. So our data set was kindly provided by Barry Stoddard and David Baker, and it consists of two sub-data sets of 5 protein structures that were designed using the Rosetta program. As shown in the previous presentation. 2 of these proteins were co-crystallized with the 17-hydroxy progesterone that we call 17-OHP, and 3 of these proteins were co-crystallized with the ligand 25-hydroxy cholecalciferol, abbreviated as 25D3. Unlike other protein challenges that we had so far, in these data sets, the ligand stays the same. It's called 17-OHP in this case, shown on the right. And it is a designed protein that differs by 18 mutations. And for the sake of the challenge, we changed the naming of the proteins. And as you can see below the protein structure, our proteins are called PL2016-1-O-1, and then the second one is -1-O-2. And what makes this data set interesting is that there is a 250-fold difference in affinity between the KDs, despite having low RMSD of the protein and the ligand, and also high sequence identity between the two. Similarly, in our second subset, the ligand also stays the same, 25D3, shown on the right, and it is a design protein that differs by 13 mutations. And again, the sequence identity is very high between the 3 proteins, and we have low protein and ligand RMSD. In the case of the 25D3 data set, we had a 4th affinity that we included in our challenge, which is the vitamin D3 of 2 macromolar affinity, but despite not having a crystal structure for this molecule. Given the data set provided, we designed the challenge where participants were provided protein structures with the co-crystallized ligands that deleted and all the waters retained, and SDF files for ligands for all 3 ligands, 17-OHP, 25D3, and vitamin D3. And participants were instructed to provide at the end of the challenge their predicted poses of the following of the 5 complexes for which we had crystal structures, which are 2 proteins bound to 17-OHP and 3 proteins bound to 25D3. And participants were allowed to provide up to 5 different poses as a result for their post-prediction calculations. And then for the second part of this challenge, we instructed participants to provide their predicted affinities, scores, and affinity rankings for the protein-ligand pairs for each of these 2 data sets. And since we had also the affinity of vitamin D3, we also asked participants to rank vitamin D3 among the 25D3 sub-data set. And what makes the challenge interesting is that the OHP data set had a 250-fold difference in affinity, even though the poses were very similar and with a few mutations and fewer crystal waters in the binding site. And in the case in the 25D3 data set, we had also a 6-fold difference in affinity between vitamin D3 and the first protein ligand complex with 25D3. And well, we wanted to see how well participants could do in predicting the poses and the scoring of these ligands at the end of the challenge. So next, I'll be going over our challenge results. We had about 15 different participants that participated in this challenge. They used a wide range of different methods, going from standard methods like Glide, SP, VINA, and GALT, to using all different types of parameters and rescoring their ligands using various knowledge-based scoring functions, and MMGPSA and PPSA. So in this slide, we're looking at how well participants have performed in determining the pose of each of the ligands. Where for 17-OHP we had a total of 16 participants, and for 25D3 we had a total of 13 participants. And the x-axis of these graphs below are the different submissions from each of these participants. And here we show the RMSD of their best pose, which we show the interquartile ranges of the RMSD of their best pose, where in red is the second quartile of the different RMSDs of the poses submitted by each participant, and Q3 in green is the third quartile range of those RMSD ranges. And between the two interquartiles, we have the median value, which is shown between the two interquartile ranges. And the left graph is the 17-OHP results, and the right graph is the 25D3 results. And we can see from these values is that participants have performed very well in this challenge, except for a few deviations in the results, and that might be due to the various parameters that were used and the different methods used as well. And we also looked at, we also were wondering how well participants have done for each of the ligand protein complexes. So in these graphs here, we look at each protein ligand complex, and these interquartile ranges show the RMSDs of the best pose from all participants for this specific protein ligand complex. Where again, in green we have the second quartile, in purple we have the third quartile, we have the median value in between, and then the whiskers are the minimum and the max value of the RMSD calculations. And again, we don't see any clear difference between the different protein ligand complexes, and the majority of participants have performed pretty well in all 5 protein ligand complexes, with less than 1 and 1.5 angstrom in RMSD for the post predictions. For our second set of calculations, we also looked at the scoring evaluations for the participants, and here we use Kendall-Taus to look how well participants have scored the different ligands. So if you have a Kendall-Tau of 1, means they perfectly scored the set of ligands. If you have a Kendall-Tau of -1, then you've scored the ligands in reverse. And since in our data set we only had 2 ligands for each of the sub-data sets, for 17-OHP we only had 2 ligands, and for the 25D3 we only had 2 ligands with actual affinities that we could use for our analysis. In that case, the Kendall-Taus can only be 1 or -1. You score the ligands right or not, and you had a 50-50 chance of determining the ranking of these ligands. And as you can see, we have at least in both data sets, more than half of the participants have scored the ligands perfectly, with 13 out of 17 participants for the ligand 17-OHP and 9 out of 15 for 25-OHP. So in conclusion, this was essentially a self-docking challenge, and that would explain the good performance across the various methods used, where we had an average mean RMSD of the best poses of 0.9 for 17-OHP and 1.5 angstroms for 25D3. And again, for the scoring predictions, we had more than half of the predictions ranked the ligand scores correctly in both targets. Thank you very much for your attention. I'll be happy to take any questions at the Q&A session.